Okay, in this lesson we're going to look at intervals of increasing and decreasing for a function and the first derivative test. Since we have done intervals of increase and decrease, we're not going to talk about that a whole lot in this video. Here it is again in case you forgot. A function increases when the derivative is positive. A function decreases when the derivative is negative. And that is stuff that we have done, I won't say extensively, but we've done it enough to where you should know that, and we've talked about it enough. So we'll move on to the first derivative test. And what the first derivative test does is, if you have a critical number, the first derivative test tells you whether that critical number is a local max, a local min, or neither. And the way the first derivative test is, it looks at the intervals of increase and decrease to figure that out. For example, the game plan, let's just pretend that f prime of 3 is equal to 0. And I do my little sign analysis, a little chart where I plug 3 into on the number line, and I'll say, okay, the derivative is 0 at 3. And then we pick test points on the left and right. Let's say to the right of my critical number, my derivative is positive, and to the left, my derivative is negative. Well, based on that, I can see that the derivative is negative, so my function decreases, and then we have a slope of 0, and then the derivative is positive, so my function increases. So since my derivative goes from negative to positive, that must be a local minimum, and that conclusion was made by the first derivative test. We looked at the signs of the first derivative to conclude that that would be a local minimum. And so the first derivative test defined in writing, if your derivative, if you have a critical number at c, and your derivative changes from positive to negative, so if your derivative changes from positive to negative, that means slopes change from positive to negative, and if slopes change from positive to negative, then you have a local max. And the previous example I just did was local min. If the derivative changes from negative to positive, the derivative changes, that means slopes change from negative to positive, therefore we're looking at a local minimum. And that is what your first derivative test is. And so we'll do a few examples of that. Now let's do the first derivative test for this function, determining where our local extrema are. And so what I'm going to have to do first is find critical numbers. So let's find the derivative. Hey, there's the derivative. And I'm going to go through these kind of fast to keep the video short. So if you need to pause it periodically to catch up with me, but you should know how to do the power rule by now. We need to find critical numbers, so we'll set that equal to 0 and find the critical number. So I'm going to factor and solve that. Okay, so I just did that real quick, so I factored out the 2x, and you get 0 and 1/6. And now we do the little number line thing, and we're going to find when the function is increasing or decreasing. So I have 0 and 1/6, and both of those are zeros for the derivative. And I'm going to plug test points into the derivative, so something to the left of 0, like maybe -1. Something between 0 and 1/6, that's kind of a pain. We'll have to go with like 1/12. And then something after 1/6, like 1. So I'll plug in -1 to the derivative, and I usually use the factored form. 2 times -1 is negative. 6 times -1 minus 1 is also negative. So that's positive. If I plug in 1/12, 2 times 1/12 is positive. 6 over 12 is a half. Minus 1 is negative. And if I plug in 1, 2 times 1 is positive, 6 minus 1 is positive, so we'll get a positive. So now I know where my function is increasing or decreasing. That's not what I wanted to know. I wanted to know where the local extrema are. And what I can determine here is, since my derivative changed from positive to negative, my function goes from increasing to decreasing. There's a local max at x equals 0. And at 1/6, my derivative is negative, so my function goes from decreasing to a positive derivative, so my function is increasing. If you go from decreasing to increasing, there's a local min at x equals 1/6. And if I want to know where local max is, the x coordinates would answer that. If I want to know what the local max is, then we would plug in to get the y coordinates. So if I asked you for the actual coordinates, we would need to plug in to get the y's also. But this is going to be our answer for now. So local max when the derivative changes from positive to negative, that is your first derivative test. and a min at 1/6. Let's see, what's the next one? Okay, here's a trig one. I gave you an interval on this one because the graph of cosine x has an infinite number of max and mins, so I gave you an interval to kind of cut off your answers there. So, let's see, 1/2 minus all that stuff. Let's see, ooh, this is a weird interval for this problem. Interesting. All right. So we will start with the derivative, f prime of x. Derivative of 1/2 is 0. Derivative of negative cosine would be positive sine x. And I would set that equal to 0 and solve. Now I'm only solving on the interval 0 to 2 pi. X sine is equal to 0 at 0, pi, and 2 pi. But these 0 and 2 pi are the ends of the interval, and you cannot have a local extrema on the end of an interval. Absolute extrema, that's okay, but locals, we can't. So what I will do is I will make a little number line. I will put my critical numbers. I'm going to go ahead and include 0 and 2 pi, even though those are not going to be answers for the problem, but it at least gives me an idea of where I need to plug in points. I'm going to plug in something between 0 and pi, like I think pi over 2 would be a great option, and something between pi and 2 pi, like maybe 3 pi over 2. And if I plug those in, sine of pi over 2 is 1, that's positive. Sine of 3 pi over 2 is negative 1, that's negative. And based on that, my function has a positive slope, then a negative slope, a positive slope, then a negative slope. That's a local max. That is your first derivative test. So local max at x equals pi. Yeah. And if I ask for the y-coordinate, you would plug in pi here. And that would be what? 1 minus negative 1, so it would be 3/2. Maybe. All right, let's see. Ooh, we're getting a little bit trickier. Find the derivative of this one, and you have to keep your eye out. Don't forget things like chain rule. We have to bring down the 2/3. X squared minus 4 to the negative 1/3. And then times the derivative of the inside is 2x. And since I'm not through with this problem, I'm going to clean this up. We're not simply finding the derivative, we are using the derivative. See, 2 times 2x is going to be 4x over, and I'm going to move this stuff to the bottom, x squared minus 4 to the positive 1/3. In the denominator, I'm going to set that equal to 0. And let's see, we have to find critical numbers. My derivative equals 0 when the top is going to be 0, so that's x equals 0. That is a critical number. But we have to be aware of the denominator also, because if your denominator is 0, those are also points of interest, things you have to be concerned with. And my bottom is going to be 0 when x is equal to plus or minus 2. So I'm going to make a little note that f prime of 2 and f prime of negative 2 do not exist. Neither one of those exist. So those are also interesting points. Can you plug 2 into my original function? See, 2 squared is 4, so I'd have 0 to the 2/3. That's okay. If I plug in negative 2, that point works also. So the derivative does not exist, but my function does exist, so x equals 2 and negative 2 are still critical numbers. We're going to put those on our number line. Let's see, so let me do that real quick. I've got my number line set up. And above your critical numbers, make note of what's happening on the derivative. At negative 2 and 2, my derivative does not exist. And at 0, my derivative is 0. So I like to put those there. If I plug in negative 3, 4 times negative 3 is negative. 3 is always positive, but see, negative 3 squared minus 4 is positive. And if you raise that to any exponent, it's still positive. So that part of the interval is negative. Plug in negative 1. 4 times negative 1 is negative. That'd be 1 minus 4 is negative 3 to the 1/3. Negative 3 to the 1/3. You can do that, and that would be a negative number, the cube root of a negative number. So negative divided by negative. If I plug in 1, 4 times 1 is positive. 1 minus 4 is negative 3, and the cube root of that is still negative. So positive over negative. And if I plug in 3, 4 times 3 is positive. 3 squared is 9 minus 4 is positive. So that's positive. And then looking at this number line, we have several places. And now remember, the derivative does not exist, but my function does exist at 2 and negative 2. So my derivative changes from negative to positive. That is a local min. So we have local min at x equals -2, and another one over here at 2, my derivative changes from negative to positive, and at x equals 2, and then I have a local max at x equals 0 because my derivative changes from positive to negative. So there are our local extrema for this one. So let's see. So at -2 and 2, my derivative fails to exist, but my function does exist. So what we're looking at there is going to be a corner or a cusp. My function exists, but my derivative does not. So I'm guessing this function does something like this. I don't know. That's a guess. Local min at corner. I don't know. Just random guess. We'll talk more about that stuff later. All right. Let's see. How many problems more are there? 2 more? I think there's 2 more. All right. How are we doing on time? 10 minutes? I guess that's okay. This one, let's see. Something I'm going to make note of right away before I even start calculus. I'm not going to do the derivative yet. I'm going to make a little note to myself that 0 does not work in my function. So x cannot equal 0. It's not in the domain. So let's be aware of that. You want to notice things like that at the beginning because sometimes that can come back to bite you at the end. So I cannot let 0 be one of my local max or mins because my function does not exist, vertical asymptote. And then before I do derivatives, this is a cute problem. Y'all have an STD. Did you notice that? Did you notice you have STDs? I'm going to change this to x to the 4th over x squared. Get rid of that single term denominator. Plus 1 over x squared. Clean that up. X squared plus x to the -2. And then I will find the derivative of that. So f prime of x is going to be 2x minus 2x to the -3, right? Then we'll set that equal to 0, and we need to solve that equation. So let's see, that's 2x minus 2 over x cubed. We have to solve that equation. How would you solve that? How would you solve that? I think I'm going to get a common denominator on the left side. I can't decide how I want to do that. I'm going to multiply this by x cubed and x cubed on top and bottom. That would give me, what, 2x to the 4th minus 2 all over x cubed. Right? And then I'm going to set my numerator equal to 0. So I'll factor out a 2. I have x to the 4th minus 1. Right? And that thing is going to equal 0 at x equals 1 and -1. And 0 is still a vertical asymptote. That's an interesting point. So I'm aware of 0. I'm aware of 0. It's not a critical number, but it's still something you want to be aware of in this problem. All right, so let's see, I shrunk that up to give me a little bit more room to work. So on my number line, I'm going to plot the points. -1, and that gave me a 0 for my derivative. 0 is a vertical asymptote for my function, so I'm going to make a little note of that. And 1 is a 0 for my derivative. And then we'll do the number line. I'm going to pause it while I do the number line. Okay, so there's our number line, and then looking at this to find my local extrema, I had a critical number at x equals -1. Derivative changes from negative to positive, so I have a local minimum at x equals -1. Now, at 0, my derivative changed from positive to negative, but that's a vertical asymptote. There is no local extrema there, so make sure you don't include that with your answer. And then if I plug at 1, my derivative goes again from negative to positive, so that is also a local min there. So we have 2 local minima, no local max for this problem. And there we go. Very good, very good. One more problem. This one, and this one has a cute little algebra trick to it, and that's why I wanted to do this one, and this is the last one. It is a product rule, so we're going to do the derivative here. So f prime of x, I'm going to assume you can do the product rule, so I'll pause it while I do that. All right, so here's our derivative. Now I went ahead and cleaned it up. I did notice there's a chain rule also with the product rule. But here's my derivative when I cleaned it up. Now what I have to do is set this equal to 0 and solve. And there's a little trick we're going to do to this one. We're going to factor it. And looking at this, the thing that I see I'm going to factor is each problem, or each one of these terms, has a 6 minus x in it. So what I'm going to do is factor out a 6 minus x, and you always factor out the one with the lowest denominator, or lowest exponent. So I'm actually going to factor out a 6 minus x squared from this whole thing. And if you're paying attention, you notice they also have an x in common. So at the same time, I'm going to factor out an x. So 6 minus x times x is going to be pulled out. And then when I factor those out, I'm left with a 2 in this first term. And that was 6 minus x cubed, so I still have 1, 6 minus x remaining, minus a 3, it was an x squared, I pulled out 1x, and I pulled out the 6 minus x squared. And then we'll clean up the inside of that. All right, so we clean it up, and then we find the zeros. So that's going to be x equals 6, x equals 0, and x equals, move 12 over, divide by 5, 12 fifths. That's kind of a silly number. And then we'll do our number line with those three. So let me set up my number line. Okay, there's our number line, and then we'll start plugging in. Plug in -1. I'll plug into my factor derivative. Now my first one is something squared, so that's always going to be positive, times x, which is -1. 12 minus 5 times -1 is positive, so that's going to be a negative. At 1, 6 minus 1 squared is positive, times 1, which is positive. 12 minus 5 is positive, so that's all positive. Plug in 3, 6 minus 3 is positive, or when you square it, still positive. 3 times 5 is 15, 12 minus 15 is negative. Then if I plug in 7, 6 minus 7 squared is positive, 7 is positive. 12 minus 5 times 7 is negative. And looking at this, we have 0 is a local minimum, derivative changed from negative to positive. So I have a local min at x equals 0, a local max at x equals 12 fifths. My derivative changed from positive to negative. 6 is a critical number, but I'm negative, and then I'm negative afterwards. So that's probably an inflection point. My guess is what happens graphically is my function decreases, levels off to a slope of 0, and then decreases again. So that's probably what's happening at 6. And if we wanted to play with the second derivative, we could figure that out. But here's what we have for number 5, and I'm done with the first derivative test.